Hi, today we're going to talk about electromagnetic fields, EMFs, find out what generates them, where they come from, what they do, what they're about, and just find out a little bit more about them as a background. So in this animation here, we can see there's electromagnetic field. It's got two components. There's an electrical field and associated magnetic field at 90 degrees to it. And you can see them being generated as they go along there. So if we do this without the movement, you can see we've got the wavelength here. So if we're looking at the electrical field in the red, you can see sort of the curve goes along, back, up and down again, and that's the wavelength. And as you can see, the electrical field is at 90 degrees to the magnetic field. And we've got the direction of propagation going along here. So what are EMFs and where do they originate? We tend to automatically think of EMFs that naturally radiate from the sun and cosmic rays, but they also radiate from everything, all the way down to individual atoms. This includes us too. We're electromagnetic. That's why if you see some of the police programs, when they're trying to catch criminals or people they're trying to track in the dark, they can use infrared cameras because we are emanating infrared, which is heat, and that's an EMF, and so we can be tracked. We're emanating it, so it extends from our body, but it's also, we're generating electromagnetic fields within ourselves as well. So EMFs can be artificially generated too. And they're used for a variety of functions. They automatically think of telecommunications, can be used for imaging, for x-rays, for diagnostics, cooking, obviously microwave ovens, and even induction cooking, electric hobs and all the rest of it too. And of course there's therapeutic use. So there's the microcurrent stimulation. There's also gamma rays for radiotherapy. So EMFs are also known as electromagnetic radiation. And with the amount of increased electromagnetic radiation and electromagnetic fields that we have now, but they've also developed new names such as electrosmog and electromagnetic pollution. Of course, smog came from heavy pollution, smoke in the air from the industrial times in the early 20th century, 19th century as well. And if we could actually see all the electromagnetic radiation, we would be something akin to that as a pea super of electromagnetic fields. So there are different types of EMFs, and they have different properties depending on their physical properties, which is linked to their energy, their wavelength, and their frequency. So we're going to go into some of these things in a little bit more depth now. So here we have a sort of diagram of a typical atomic structure. We've got the nucleus in the middle here, which is made up of protons, which are positively charged, neutrons, which are neutrally charged, and then we've got electrons, which are in these orbits around the nucleus, and they're negatively charged. Diagram here, the nucleus looks relatively large in comparison to the orbits, but actually there's most of what goes on, the volume of an atom really is space. These orbits are very much further away from the nucleus in reality. So this is very much a diagram of idealized to make it easy to see. So all atoms generate characteristic electromagnetic fields. The electric fields are generated by the charge difference and separation between the nucleus, which is positive here, and the surrounding electrons, which are negative, and that sets up a static electrical field. There doesn't have to be any movement involved for that to happen, although obviously with electrons circulating around there is movement as well. When everything is above 0 Kelvin, which is absolute zero, minus 272 degrees centigrade approximately, atoms and electrons are vibrating, they're spinning, and they're rotating, and it's this movement which generates the magnetic fields. So this is again a diagram of electron spin, how they generate magnetic fields. So we've got electron, it's spinning in this direction, which gives us a north down below and a south up above. But obviously if it spins in the opposite direction, then you get the magnetic fields, the poles are at the other side of the electrons here. So we're getting electrical fields, but we're also getting magnetic fields, hence the term electromagnetic field. So if we look at these a little bit more in depth, so we get, this is a table of frequencies. So if we look at carbon bonds here, carbon to hydrogen, carbon to deuterium, and carbon to carbon. So as these atoms get heavier here, the frequency goes down and the energy goes down, and so does the frequency as well. In this second group of three here, we've got a single carbon to carbon bond, double carbon bond, and a triple carbon bond. And of course, as these go down, the bonds get shorter, and the bonds get stronger too, and the frequency goes up. So the frequency and wavelength of the emitted radiation is determined by the strength and the length of the bonds between the atoms and the atomic masses at each end of the bond. And there's a law which sort of links all these in an equation which is called Hooke's law. So all these things are very well accepted. It's very mainstream science. There's nothing weird or wonderful about anything that we've said so far. So if we look at another table, which is looking at the covalent bonds, which is the bonds between different atoms. Again, it's looking at the energy of these bonds and also the length of the bonds. And this is also then what helps to determine the frequency and the wavelength of the energy that's emitted from molecules and from atoms as well. But these bonds also have what's called a resonant frequency. And they will absorb energy which comes in at this resonant frequency and accumulate it. And if the energy is high enough, it will be sufficient to break the bond and separate the atoms. So if we look at the electromagnetic spectrum as a whole, because it is a spectrum, you can see the wavy line here, which isn't little blocks, it's actually a continuum that gradually the waves get shorter and shorter and shorter, and the frequency gets higher and higher and higher. So, but we have put arbitrary categorizations on top of this electromagnetic spectrum. So at the bottom we've got extremely low frequency, we've got very low frequency, radio waves, microwaves, infrared, visible, ultraviolet, X-ray, and gamma rays. You can see typical examples of what they're used for and articles which generate them. So we've got power lines here at the extremely low frequency, VDUs as just low frequency, radio waves, and TV, and then mobile phones, microwaves, and radio as well. So then we've got infrared, the sun obviously, and the visible light spectrum that we can see. So we can actually only see quite a small band of the electromagnetic spectrum. There's a lot more outside it that we can't see. Obviously the ultraviolet, which is why we need sunglasses to protect our eyes, and then X-rays obviously so we can visualize ourselves, and gamma rays that obviously create nuclear power. So this is also divided into sort of two main categories of ionizing and non-ionizing, and the higher the wavelength and the higher the energy, they become ionizing, which means that there's enough energy in the electromagnetic field to actually damage the bonds and cause DNA damage in people and separate off electrons. And then we've got non-ionizing down here, which is where we use a lot of our gadgets and telecommunications happen in this non-ionizing area of the electromagnetic spectrum. And unfortunately, there was an original assumption that this was completely not harmful, but research has recently proven that it can cause biological effects, and those biological effects can be harmful as well. And you don't have to have what's called a thermal effect, i.e. a heating effect, to get these biological changes. So if we look at the electromagnetic spectrum a slightly different way, we've sort of been divided into sort of where we see telecommunications fitting in. So we've got computers down at 60 to 100 hertz, very similar to the power lines. And then we've got TV broadcasting here, radio, AM and FM. Then we've got mobile phones, smart meters, Wi-Fi, and remote controls for our TVs at sort of just under 6 gigahertz. And then we've got microwave radiation here, which is 3 to 30 gigahertz. So you can see we're gradually creeping up using higher and higher frequencies of the electromagnetic spectrum as we run out of bandwidth, as they call it, down below. So what we're adding on here isn't a replacement for what's happening in the lower frequencies of electromagnetic spectrum. We're actually adding on more and more higher frequencies as we go. So if we look at natural EMFs in a little bit more detail. So EMFs are generated naturally and can be high power, e.g. the ones we tend to think of from the sun or cosmic rays, or they can also be very, very low power, these sort of indigenous EMFs within the body that are generated by atoms and very small molecules. And even if we think about the microbiome in the body, the bacteria within us, they are communicating with themselves, with each other, and with us using these EMFs, which of course are non-thermal. So the idea that EMFs have got to be thermal to have some sort of influence on the body really just defies logic, because we are naturally producing electromagnetic fields within the body, which are having a biological effect, and yet they're not generating heat in order to do that. So natural EMFs are non-polarised and analog, so they're not pulsed. And so our body has adapted to recognize these through evolution. So if we think about Schumann resonances coming from the Earth, and also the rays from the sun. So mainly natural generated microwaves from the sun are absorbed by our atmosphere, and so we have not evolved to tolerate these. So as our telecommunications are moving more into the microwave field, we are being exposed to electromagnetic fields and frequencies that we really haven't evolved to adapt to or to tolerate, and without doing any proper experimentation to make sure they're safe, it really is madness to increase in this direction without checking for safety first. So we've got some natural EMFs, as I've already mentioned, the Schumann resonance. We've got Earth's background magnetic field as well, these are beneficial to our health. And actually, when the space station went up, or astronauts go into space, they originally didn't have any replacement for these Schumann resonances or natural magnetic fields. And so people used to get sick when they were in space, and nowadays they have sort of replacement Schumann resonances and electromagnetic fields, so that the body is, within its natural environment in terms of EMFs, and in order to keep the people up in space healthy. But of course, even what is healthy for us in excess can cause problems. So you can get excess of magnetic storms, which will often increase cardiac problems. They'll get more people going to hospital with heart attacks and cardiovascular problems when there's magnetic storms that are going on, and we won't necessarily be aware consciously that these are happening, but they are, and there'll be people who are monitoring these, of course. And also, if you think about it, if we stay in the sun too long, a little bit of sun radiation is great for us. It produces vitamin D in the body, which is healthy for us. It helps our immune system. But if we stay in the sun too long, obviously it can cause damage. It can cause melanomas and skin cancers over a period of time, and it doesn't happen straight away. It can be a cumulative effect over very many years. So we've got these natural EMFs, and of course a lot of people are trying to do shielding to cut out the artificial ones, but in doing that they'll cut out the natural EMFs as well, and then you'll end up with the same problem space guys we're finding, where actually you've cut out the natural EMFs as well, and yeah, we need these to support our health. So looking at artificial EMFs in a little bit more detail. So artificially generated EMFs are polarized in one direction, and I'll show you a little diagram of that bit later on, but it means everything's coming in a uniform way that our body hasn't evolved to recognize, and it has a problem with it when it comes in that way. EMFs are used for telecoms, are also modulated and incorporated into a carrier signal, and unfortunately a lot of the research that is done looking at the effects of electromagnetic fields on the body is just using static electromagnetic fields and frequencies, and none of these modulations are being included in the research. And of course, you know, these modulations have a big impact on how the body can respond to the electromagnetic fields that it's being exposed to. So digital electromagnetic fields have pulsed modulation rather than a smooth analog. So we get if you think about a binary system, it's either a 1 or a 0, there's nothing in between. So you get very sharp spikes and rises in pulses, and very sharp drop-off as well. And because there's no way that the body can anticipate the pattern of this, or how sudden the change of the modulation happens, this is why the body finds it very difficult, if not impossible, to actually adapt to these digital and pulsed EMFs. Here we go. Nature has not evolved within these EMFs and has not adapted to them, and we can't adapt to this on-off. It's really important. One of the ideas that have been put forward as an alternative to telecommunications is called Li-Fi, which is using light as a way of carrying telecommunications. But of course, as long as it's pulsed, it's still going to have the same problem in terms of the body not being able to adapt to it and causing problems. So artificial EMFs have increased in such a short period of time, and we are now 1 quintillion times more exposed than the natural background EMFs that we evolved in. And this has happened over 30, 40, 50 years max to this degree, and certainly it's been a pretty much of an exponential rise. So the figures we're getting now are rising even quicker than they were in early times. 1 quintillion sounds like a very large number, and it is. It's a 1 with 18 zeros, and most of this rise, as I've said, has happened probably mostly in the last 10 years. So here we got a little animation of what happens with polarization. So if we've got unpolarized light, for example, here it goes through polarized lenses, and depending in which direction that basically filters, you end up on the other side of the lenses with this polarized light, which goes in one direction, in one plane. And this is how, if you get polarized or Polaroid sunglasses, if you put one pair at 90 degrees to another, you can cut out all light, because obviously if you cross these two lenses over, one will cut out the up and down fields, and the other one will cut out all the cross ones. So you'll end up, if you put them over each other, it'll cut out all light. If we look again at the telecoms signal modulation, you see here we've got a carrier wave in the middle line of all these things. And so if you've got amplitude modulation, so we're putting this figure, this signal here on top of the carrier wave, and this is the modulated result. So again, it's quite smooth. So you know, the early AM signals, the body could adapt to them fairly well because there was a degree of pattern to it, there was a degree of predictability to it that the body could accommodate to and get used to. We go on to frequency modulation. The result here is a little bit more unpredictable, but it's still fairly uniform what's going on. And then once we go into digital modulation at the end here, these are really very sudden bands of high pulsing with gaps in between. And this is what the body finds it very difficult to accommodate to. So as I was saying, when we're doing, a lot of research has been done on electromagnetic fields. A lot of the fields that are being used are very much like this carrier signal, which of course is totally predictable, very uniform, and nothing like these modulated signals down the bottom that are actually what we're exposed to in real life. And of course, many of the researchers will be looking at one frequency at a time. In actual fact, we're exposed to that whole electromagnetic spectrum altogether, and the interferences and the cumulative and peaks and troughs just aren't being replicated in a lot of the research experimentation that's going on. Another important thing we got to bear in mind is we talked about resonant frequencies. If you remember at the beginning, I was saying that if energy comes in at the resonant frequency of a bond between two atoms, it gets absorbed. So we've got a couple of very important resonant frequencies. One is water, which is 22 gigahertz, which is very close to the high band 5G that's that will be rolled out when they've got mass very much the infrastructure more in place than they have now, and also 183 gigahertz, which probably wouldn't be used for quite some time. But we've also got oxygen, diatomic oxygen, O2, and its resonant frequency is 60 gigahertz and 118. You can see these peaks here on the graph. Unfortunately, 60 gigahertz is going to be the unregulated frequency for Y gig, and this is also going to be used within our routers, within the house. We have got no idea. Obviously, oxygen is very important for life. It's in the atmosphere, and it's important for us, animals and plants. And no testing has been done to understand what repercussions there might be for having such high levels of 60 gigahertz microwave radiation in the atmosphere, because being unregulated, it doesn't need a license. So anybody who wants to use frequency telecommunications, but without having to pay for a license, will of course be forced or will use the 60 gigahertz frequency. There's been some suggestions that it might interfere with how oxygen binds to hemoglobin. The truth is the research hasn't been done. We don't know, but it is entirely possible that there might be biological consequences of breathing in oxygen, which has been irradiated at its resonant frequency, and the electrons will be at a higher energy state from having absorbed this energy than normal, and we don't know how that's going to impact the body. Okay, well, that was a run through on electromagnetic fields, where they come from, the natural and the artificial ones, how we use them for telecommunications and how they're modulated to be used in that way. I hope you found it useful. I hope you know more about electromagnetic fields than you did when you started. If you like the video, please give us a like and look out for the next one, which will be how electromagnetic fields can affect our biology and what effect that can have on us.